Alright students, welcome to vodcast 5.3. We're going to talk a little bit tonight about orbitals. And so in the last unit we talked about the Bohr model. We're going to talk a little bit about orbitals, and this is the big setup for the real big topic that's coming up, which is electron configurations. Okay, so let's get into it. First off, from what we talked about yesterday, or maybe 2 days ago, depending on when you guys saw the vodcast, the Bohr model only works for hydrogen. So this idea of the planetary model here, where we had a nucleus in the middle, and then we've got all these sort of concentric rings around it, and each of these rings is where the electrons are. Okay, so we got electrons, buzzing around on these. That only actually works for hydrogen. You're like, oh my gosh, so what is Bohr famous for? Bohr is still, the Bohr model we still use a lot. You guys, when you're in middle school, you probably drew these rings and filled them in with electrons. So, that model is still valid. It's sort of the simplest way to talk about things. And if you're not in chemistry or some higher sciences, then you can use that. But after Bohr's model was found not to be as valid, then we get two guys, two pretty famous scientists. One of them, Werner Heisenberg. Okay, you often hear his name associated with the Heisenberg uncertainty principle, because what he says is that you can't know exactly the speed and the place of an electron at the same time. That's going to lead into the next model that we're going to talk about. And a guy named Erwin Schrödinger, who is together, these two guys, they're not really working together, but their ideas are what lead to the idea of the modern atom, which is what we call the quantum model. Okay, now quantum goes back to the idea that there are these discrete units of light being emitted, little photons, and that's sort of some of the stuff that we talked about when we did wavelength and all that. But just keep in mind that that's what quantum means. Okay, so here's the basic idea. We don't know exactly where the electrons are. This is what Heisenberg is saying in the Heisenberg uncertainty principle. Is we can't know. That electrons are so small that by the mere act of measuring where they are, we would, or measuring how fast they are or where they are, that we would change their location and speed. Okay, so the quantum model rests on this idea that if we can't know exactly where they are, that we know the probability of where they are. And that seems sort of weird and nebulous. The idea that we don't really know where they are, that there's a probability. We know with a 90% certainty that they're in a certain area. And the reason for this is the electrons are moving around really fast and they're all over the place, and most of the time they end up in these certain regions of space. Okay, and keep that sort of phrase there in your mind, the certain region of space, because that certain region of space has a certain name. Okay, and that region of space is called an orbital, and that obviously is what today's lesson is going to be about, is this idea of orbitals. Okay, so the region of space where we find electrons are called orbitals, and we're going to walk through here in a second the names of the different types of orbitals and their general shape. But just keep in mind that each of these is just sort of an area where we are likely to find electrons. They're not necessarily there, but we're usually going to find them there. You also want to keep in mind the second point, and this is going to get real important when we do electron configurations in the next unit, is that every orbital, okay, can only hold 2 electrons. We're going to have a name for that rule in the next unit, but just keep in mind as we're walking through there that they can only hold 2 electrons each. Okay, so let's start looking at them. First off, are s orbitals. They're the lowest energy area, and so like in the case of a helium or a hydrogen, they only have one possible region of space, and that is this 1s orbital. Okay, so their electrons have to be in this area, and you can sort of see here that there's some denser areas and some less dense areas in there as well, and if you take some higher science classes, we'll talk about that. What matters for us is that within an S sublevel, okay, so the letters that we're going to give here, when we say S, P, D, and F, they're technically sublevels, but within them are orbitals of that kind. In S, there's only one orbital, okay? Now, what does that mean for us? Well, that is then going to mean that if there's only one orbital, that S can only hold 2 maximum electrons, okay? And that would make sense. So 1s can hold the 1 electron of hydrogen or the 2 electrons of helium, but beyond that, we have to go up to the next level, and we would go to 2s. And so lithium would start filling up in the 2s area. Okay? So let's talk about the next region. The next region are p orbitals, or the p sublevel. And in the case of p, there are 3 different orbitals here. And the way they work is that these p orbitals sort of look, there's 3 of them. The p orbitals sort of look like, I mean, this is what they really look like. Very often they're sort of depicted as looking almost like infinity signs, or sometimes they're called dumbbells. And they're set up around the XYZ axis. Remember that everything here is 3-dimensional. And so you've got an x-axis, you've got the y-axis, and then you've got some sort of coming in, like picture that as like going right into your face, and then back into the board. And so those are x, y, and z, and that's what these are. So x, y, and z orbitals. Okay? And since p has 3 orbitals within a sublevel, that means that it can hold a maximum of 6 total electrons. Okay? So making pretty good sense so far. Here's where it starts to get really wacky. D orbitals, the next step up from p, first off, there are 5 of them, and you should be noticing a pattern now. We had, just in case you didn't notice the pattern was that we had 1s, we had 3p, and now we've got 5d, and so that sort of lets you know that the next one will be 7. Okay, and we'll talk about that in a second. But the d sublevel has 5 different orbitals that it could be, okay, and they are all kinds of weird, wacky shapes. Some of them look like sort of double p orbitals, and they're in different planes here. And then you see this one that just looks really weird. It's a torus, which is like a donut, and then it's got what looks like a p orbital sort of wedged in there. So anyway, what matters for us is that there's 5 orbitals. There's 5 regions in space for d. And so that means that there are 10 total electrons in the d orbitals. Okay? In the f orbitals, remember we said that the next one, if we're going by the pattern, 1 for s, 3 for p, 5 for d, that the next one would have to have 7, and it does. So f orbitals are next. They have 7. You can kind of look at their really extremely weird shapes. They don't, again, it's like, p times 4 or something, and then there's like only 3 lobes on these, and then they've got like a double donut thing, and then a p. It's just really weird. And remember that these aren't just like, arbitrary, like they blew up a balloon and threw electrons in there, but these are mathematically determined. It's statistically shown that the electrons 90% of the time are in the areas that are represented by these things. Okay? So for f orbitals, we have a maximum of 14 electrons then. Okay, so 7 orbitals, each orbital can hold 2, so a max of 14. Oops. Okay, so what does all that have to do with us and with the periodic table? And we're going to get a lot into this when we do 5.4, which is on electrons. But here's the main gist of it, okay? The periodic table can be divided up into blocks. And these blocks each represent an area where the atoms, or the elements in those blocks are going to end in a certain orbital notation. They're going to end in a certain orbital. So you can see how they're split up here. The first 2 columns of the periodic table are what we call the S block. Now, why is it 2 columns? Okay, because remember, each one of these represents an element that has a certain mass number, okay? It's got a certain atomic number. And the atomic number tells us how many electrons. So 1, 2, okay, so helium sort of belongs over here. We'll talk about later why it's over here. It really should go right here, but we put it here because it reacts much more like these elements than it does these. Okay, and so then if we started to fill these in, okay, what we would notice is that I've got 1, 2 electrons. That's the first s orbitals. Okay, 3, 4. So that's the second one. So every s can hold 2 electrons, and that represents the 2 columns here. So sodium and potassium, and then calcium, and so, or magnesium and calcium, and so these are the S block. They all end in S when we do electron configurations, and we'll do that coming up soon. Okay, jump over to the other side here. This region here is called the P block, and if you remember, how many electrons did we say that we could hold in the P block? Well, we said that there were 3 orbitals in P. Okay, and so if there's 3 orbitals, then that means that there are 6 electrons. 1, 2, 3, 4, 5, 6. Okay, so that means that we could end in P1, P2, P3, P4, P5, P6, and we'll talk more about that in the next podcast. The transition metals, okay, everything in here, okay, those are the D block. And remember again, the D block, we have 5 orbitals, so 10 possible electrons. And again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and again, you can probably sort of see the pattern developing. Down here in the F block, we said for the F block that there were 7 orbitals, and therefore we could have 14 maximum electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, now what does all this mean? Why does it matter? This is because the periodic table doesn't just happen to end up this way. The periodic table is arranged the way it is for very specific reasons, and those reasons are related to electrons. Okay, now you're thinking, we just watched a video where it said that the reasons were related to atomic number and properties. Okay, and exactly, that is precisely correct. But what we're going to see is that what determines the properties, okay, and the atomic number to a lesser degree, but what determines the properties is the electrons. And so everything that is in the S block, the first column here, they react very much similar because they all end with 1 electron in the S. All of the halogens over here in group 17, they all react pretty much the same way because they all end in the same 5 electrons in P. Okay? Now we're going to get a lot more into that, but I wanted you to know what the orbitals look like, and where they are, what they're called, and how they relate to the periodic table before we dive full bore into electron configurations. All right? Thanks a lot, guys.